Hello and welcome everyone. In this class, we shall solve exemplar problems. First one, find the principal argument of the complex number 1 plus I root 3 whole square. The argument of the complex number z, x plus iy, is given by this table. Theta is the argument of z, where alpha is tan inverse of modulus of y by x. If z lies in the first quadrant, theta is alpha. If z lies in the second quadrant, pi minus alpha. When the complex number lies in the third quadrant, its argument is theta minus of pi minus alpha. If z lies in the fourth quadrant, it is minus alpha. Let z equal to 1 plus I root 3 whole square. Now theta, the argument of z, argument of 1 plus I root 3 whole square. Here, use this result. Argument of z power n is n into argument of z. So the power comes out 2 times argument of 1 plus I root 3. That is 2 times. Here both x and y are positive. Directly we can write its argument tan inverse of modulus of y by x. That becomes 2 times tan inverse of root 3 by 1 root 3. That is 2 into pi by 3, 2 pi by 3. In this question, we are asked to find z, given that modulus of z is 4 and its argument is 5 pi by 6. Polar form of a complex number is z equal to r times cos theta plus I sin theta, where r is the modulus of the complex number, that is given to be 4 here. Theta, the argument is 5 pi by 6. Just we need to substitute these in z equal to r times cos of theta plus I sin theta. Z is 4 times cos of 5 pi by 6 plus I times sin of 5 pi by 6. We know that cos of 5 pi by 6 is root 3 by 2. Sin of pi by 6 is 1 by 2. So here we need to find the value of cos of 5 pi by 6. 5 pi by 6 is 30 degree. 5 times that 150 degree. 150 degree lies in the second quadrant where cos is negative. So we can directly write minus root 3 by 2. But in second quadrant sin is positive, just write 1 by 2. So that is multiplying, we get minus 2 root 3 plus 2i. Next question is, what is the conjugate of this complex number? Let us take this as z. And here we shall use these results. Conjugate of z power n is conjugate of z whole power n. And conjugate of the quotient of two complex numbers is conjugate of the numerator upon conjugate of the denominator. So we can write this as conjugate of z is 2 plus I upon 1 minus 2i becomes 1 plus 2i whole square. Now you expand this in the denominator. A square plus b square plus 2ab. That becomes 2 plus I upon 1, I square is minus 1, 2 square is 4. So minus 4 plus 4i. That is 2 plus I upon minus 3 plus I 4. In order to express this in the form of express Iy, use this method. Suppose you have a plus ib upon c plus id. The real part and imaginary part. Denominators of both will be c square plus d square. That is sum of the squares of real and imaginary parts of the denominator, c square plus d square. For the numerator of the real part, so you take product of the real parts plus product of the imaginary parts. That will be AC plus BD. You cannot ignore the signs here. For the imaginary part, you take minus of determinant AB, C, D. That is AD minus BC. That is AD minus BC. That is product of A and D minus product of C and D. Now 2 plus I upon minus 3 plus 4i. Denominators of both real and imaginary parts, square of minus 3, 9, square of 4, 16. Here also you get same. For the real part, take the product of this and product of this. Here coefficient of I is 1. That will be minus 6 plus 4. Imaginary part minus of. Now you take the product of these two. 2 into 4, that is 8 minus product of minus 3 into 1. Minus 3, that becomes plus 3. So finally you get the answer as minus 2 upon 25 minus I11 by 25. Next question is, if a square plus 1 whole square upon 2a minus I equal to x plus iy. What is the value of x square plus y square? We know that x square plus y square expression appears when you take the modulus of this complex number. So here observe a square plus 1 whole square is not a complex number, is a real number. So if you take the modulus of that, you will get the same thing, a square plus 1 whole square. Modulus of a square plus 1 whole square upon 2a minus I equal to modulus of x plus iy. As I mentioned, numerator is a positive number. Its modulus will be the same, a square plus 1 whole square upon root of 2a whole square plus 1 square. That is root of x square plus y square. Remember, modulus of x plus or minus iy is always root of x square plus y square. Now squaring on both the sides, we get a square plus 1 whole raised to the power of 4 upon 4a square plus 1 equal to x square plus y square. This is the required answer. Next question is, where does z lie if modulus of z minus 5y upon z plus 5y equal to 1? We can write this as z minus 5y equal to modulus of z plus 5i. Further, z minus 5i equal to modulus of z minus 5i, which is of the form modulus of z minus z1 equal to modulus of z minus z2, which always represent a perpendicular bisector of the line segment joining the points representing the complex number z1 and z2. So here z1 is 5i on comparing, z2 is minus 5i. Corresponding to this complex number, we have a point 0, 5. Real part is 0, imaginary part is 5. And z2 represents the point 0, minus 5. These 2 points lie on the y-axis. Here A, this is B. 0, 5 and 0, minus 5, the origin. O is the midpoint of AB. So the perpendicular bisector is the x-axis. So therefore, Z lies on x-axis. That is real axis. Now, in this question, we need to find the real value of theta for which this complex expression is a real number. Let z equal to 1 plus I cos theta upon 1 plus I times, you can write this as minus 2 cos theta. If this complex number is a real number, then its imaginary part is 0. Imaginary part of z will be 0. What is imaginary part? Minus, in the denominator you get sum of the squares of real and imaginary parts. That is 1 square is 1 plus 2 cos theta whole square, 4 cos square theta. In fact, we don't have to write the denominator. Now in the numerator, product of these two. So that is 1 into minus 2 cos theta minus 1 into cos theta. So you get this as minus of minus 2 cos theta minus cos theta equal to 0. If you cross multiply, you get 3 cos theta is 0. That gives us cos theta equal to 0. The general solution of cos theta equal to 0 is 2n pi plus or minus pi by 2, because cos pi by 2 is 0, where n is any integer. Or by inspection, when you take n equal to 0, the value of this expression becomes just pi by 2. If you take the value of theta as pi by 2, here cos pi by 2 is 0, here also 0, then this becomes purely real number. In fact, that will be 1. Very similar problem, the value of alpha for which the expression is purely real. So this expression will be purely real only when its imaginary part is 0. So the imaginary part of this complex number z First, let me write this as 1 plus I into minus sine alpha on 1 plus I into 2 sine alpha. So the imaginary part of z must be 0 for z to be purely real. So in the denominator, you get 1 square plus 4 sine square alpha. In the numerator, product of this minus product of this. In fact, here you get minus of 2 sine alpha, minus of minus sine alpha becomes plus sine alpha. That is 0. Now that gives us 3 sine alpha equal to 0. Sine alpha is 0. That is sine 0 is 0. So therefore, general solution of alpha is n pi, where n belongs to z.